Okay, so sorry, I got cut off there. So let's take a look when we increase the temperature. We'll double it. So what you're going to notice is, okay, so not only are the molecules moving faster, but also when your green and blue collide, the chances of them turning red are very high. Whereas before, when we had the lower temperature, the green and blue, once they collided, still may not have created red. Okay, so what's happening when we increase the temperature? Two things. Number one, we're increasing the number of collisions because it's going faster. And number two, the percent of collisions that are becoming successful are higher because we have more energy in our particles. So they have enough energy when they actually collide to be successful. So let's continue on here with our note. So that's temperature. So concentration is essentially talking about how many particles you have or molecules you have in a certain amount of solution. So for example, going from left to right, we can see that the one on the left has more particles than the one on the right has more particles than the one on the left. So what's happening here is you have more collisions because there's simply more particles that are there. And that kind of makes sense. If there's more particles, you're going to have more collisions because there's more stuff in the way. So while the particles are kind of bouncing around, they hit something. Whereas if you have, so this is called a high concentration. So high concentration just means you have more particles that are there, right? So automatically there's going to be more collisions. Over here we have a low amount of concentration, so there's less particles, so of course there's fewer collisions. So notice we're not changing the energy. There's no energy change here. This is not like temperature. It's just energy being the same, and you have more particles, so you have more collisions. So let's take a look at our simulator again. Still have it going from before. So we'll stop this. So we'll set this up, and I'm going to go back to the temperature we originally had, and so you can compare it. So we'll look at this again. So notice, right, you won't always have your particles colliding and making red. Let's see if we can zoom in on some here. Of course, again, we're not, oh, there was one. So that green and blue collided, but it did not make red. So let's stop this. And we're going to set this up, and we're going to double the amount, not the size. We're going to double the amount of green and blue to start with. So meaning we're basically doubling the amount of particles that are here. So you can see there's automatically more particles, which means that when we actually have the collision start, right, they're still moving at exactly the same speed, but just naturally you're going to have more red product because you have just more particles reacting. You're not changing the percent of success. So let's say you had, 80% successful collisions. You're still going to have that. It's just that there's more collisions happening, so there's more product that's made. Okay, so that's concentration. So temperature affects both the energy and the collisions. Here we have just the collisions being affected. Okay, so surface area is essentially focused on solids only. So when we look at surface area, this can only really impact when you have a solid that is in your reaction. So what this means is, so of course, let's say we have a big chunk of a solid. The reaction can only happen on the surface of that particle or of that chunk. So let's say we have like a big piece of marble in this case. Marble can only react with the outside part that is exposed, right? But if you were to make the particles smaller, so let's say we took that marble piece and we crushed it up into small little chunks, what happens is the reaction now can happen faster because there's more marble that is exposed on the outside, right? So what this is doing here, what we're calling this term, is that there's been an increase to the surface area of our marble. So meaning the amount of exposed surface has gone up because we're able to go in around each piece of marble. Okay, so I compare this to, let's say you were cooking a steak versus ground beef. Okay, so they're made up of the same thing, except steak, you have like a big chunk of it. The only part that's being cooked is the outside part, right? It takes longer to cook the inside because heat can only be exposed to the outside surface. Whereas ground beef is essentially little pieces. So it's like you took the steak and you ground it into smaller chunks. Now this can cook a lot faster because the heat is essentially touching all of these little portions. So when you increase the surface area, you're basically making the particle size smaller, so the number of collisions are going up. So again, this is affecting the number of collisions, right? So going from this large piece to the smaller pieces, your collision number is going up. And lastly, we have a term, this may or may not be new for you. So we have a term called a catalyst. So a catalyst is essentially something that is added to a reaction that does not, it's not actually a reactant or a product, but what it does is it allows the reaction to go faster. Okay, it's kind of like a reaction helper. So how does it help this reaction go faster? So what happens is it reduces the amount of energy that is needed for that chemical reaction. So if you remember, there was two things that had to happen. You had to have your particles colliding, and you had to have enough energy. So what a catalyst does is it lowers the energy requirements. So let's say originally, so with no catalyst, let's say a reaction needs 25 joules of energy. So obviously I'm just making up this number. Joule is a unit of energy, but I'm just making up the 25. With a catalyst, just to give you an example, maybe now it only requires 20 joules. So what that means is before, if I had two particles colliding with 20 joules, before there would be no reaction. But now with the catalyst, if they collide with 20 joules, there will be a reaction. So essentially what this does is it does not change the number of collisions, but what it will do is it will change the number of successful collisions because it lowers the amount of energy needed. Okay, so this is just a graph showing you energy representation. So this is the reactants and then the products. So what this graph is showing you is this black line is showing how much energy is needed for the reaction without a catalyst. Yes, it's uncatalyzed reaction. So let's say this was our 25 joules. So that means if the reaction did not have 25 joules, no product would be made. So what this green line is showing is the catalyzed reaction. So meaning with a catalyst, maybe now the requirement is 20 joules. So the amount of energy that is needed for the reaction to happen is lower, which means you can have more product that's made faster. So again, this is not changing the number of collisions. What this is really doing is changing the amount of successful collisions, because when they collide, they don't need to have as much energy for the product to be made. Okay, now when we're writing out a chemical reaction, they're always written in the same way. Okay, so you have two parts. So you have an arrow that is separating the two sides of this reaction. So everything that is on the left side of the arrow is called a reactant. And I've been using this term already a lot. So a reactant is something that is a starting material. So it's like the items that are being, before the reaction begins. A product is everything that is on the right-hand side of the arrow. So in this case, this is showing two reactants are coming together to make two different products. The order that this is in does not matter. What matters is reactants have to be on the left, products have to be on the right. So whether or not you wrote the reactants in opposite orders here, that doesn't matter. Same deal with products. What matters is, though, you have to keep the products on the correct side. Okay, so there's two ways we can represent a reaction. We can write it in words, or we can write it with chemical formulas. This is why we went through, we reviewed nomenclature at the end of Unit 1, because when we're writing out chemical reactions now, you have to be able to go from the word to the chemical equation and vice versa, So here's an example of a word equation. So this is where you have the reactants and products written out with their names. So you're not writing the formulas in. So here you have copper plus silver nitrate produces silver and copper 2 nitrate. So it didn't matter. So going back to what I was saying before, it doesn't matter if I say silver nitrate plus copper, making copper 2 nitrate plus silver, right? The order of this doesn't matter. What matters is it's on the correct sides. So if you had to convert this into a formula, this is why we went through all that nomenclature. So silver nitrate, right? You would have to write out the formula for silver nitrate. Again, like following crisscross rule, understanding a polyatomic ion, all that good stuff that we learned about is basically starting to come into play. So here's what it looks like in a chemical equation. So what we're doing now for chemical equation, this is the exact same reaction, by the way. So chemical reactions in grade 11, when you're writing them out, by the end of this unit, you will understand all of the different subscripts to be written, which tells us the state of matter. So here we have copper and silver nitrate, silver and copper 2 nitrate. But notice there are little subscripts that will tell us the state of matter that this compound is in. So you'll see them quite often, and actually, like I mentioned, we want to start practicing to do this. You'll learn a little bit more as we go through this unit, but by the end of this unit, every reaction you are writing for me will have these subscripts. So the little s represents solid. So notice copper is a solid and silver is a solid. It makes sense, they're metals. Little l, a little lowercase l, is liquid. A little g is gas. And AQ represents aqueous, which we've seen already when we looked at acids. This means dissolved in water. So you're probably thinking, well, AQ is only used for acids. And that's not true. It's for anything that is dissolved in water. So you'll notice here, silver nitrate is dissolved in water. And copper 2 nitrate is also dissolved in water. So like right now, you don't know that this is aqueous because you haven't learned about it yet. So obviously this is what I mean. As we go through this unit, you'll learn when do you write AQ or not. Okay, so right now, so this is the big question. How do I know what the state of matter this is in? So we are going to be learning them, okay? But there are some states that I expect you to know right now. Okay, so these ones you need to know. So water is always a liquid. So when you write out H2O in a chemical reaction, you should have a little L there. Unless it's from a combustion reaction, in which case it would be a gas. We'll review that again when we get to combustion. Diatomic molecules are gases, so our Hofbrinkels are all gases, except bromine is a liquid. And actually, add to this, please, iodine is a solid. So there should be a little S. I'll write that a little bit better. Okay. Single metal elements are always solid except liquid mercury, and we already learned that acids are aqueous. So if you're writing out an acid formula, you should have the little AQ. So at this point, these are the states I want you to know. but we will learn more as we go throughout this unit.